I am Aung from Telecom SudParis. Today I will talk about traffic intensity detection using general purpose sensors. So this is the agenda that I will go through today. So firstly, I will talk about motivations. Traffic congestion is the problem that we all face. So currently, to monitor the traffic, we usually use Intelligent Transportation System or ITS. So there are several issues with current ITS system. Firstly, they usually rely on specialized sensor, for example, commonly cameras. To deploy this system, they are expensive and it is expensive to maintain as well. So for example, for camera-based system, we need high bandwidth as well to transfer the data. So more usually they are built for the single purpose only. Another problem with this camera solution is that now the people are more concerned about their privacy issues, and more and more regulations are imposed on the handling of the video data. So a privacy issue can also be challenging for the handling of the video data as well. So instead of using one specialized expensive sensor, we can use multiple low-cost simple sensor like microphone, like temperature sensor, and many things to monitor the environment. Instead of one aspect, we can monitor several aspects. So one good things about doing this is that, for example, we can deploy microphones and also air quality sensors. So we can predict, for example, from the noise level, we can predict the air pollution, or from the pollution data, we can predict back to the noise level. So by using these low-cost sensors, we can use for multiple purpose in the future. So it is, how to say, horizontally scalable. So in order to leverage these simple sensors, we need the capabilities of AI. So by deploying AI at the edge, instead of the cloud, we can do processing in more real time, and we can also reduce the latency during the inference time. So since we do the detection at the edge, we don't have to send a lot of data back to the cloud. So we can reduce the requirement for the bandwidth as well. Since we don't have to transfer a lot of data through the unsecure medium, all the securities and privacy issue related with the data transmission can also be reduced. So with this motivation, we try to investigate the viabilities of the edge computing-based and traffic intensity monitoring system, which utilize general purpose sensor like microphones and other simple sensor. So to do that, we create two edge devices, which are equipped with microphones and other sensors like temperatures and air quality sensor to monitor the traffic. So, and then we do the audio data analysis. For audio data analysis, we usually use image data analysis techniques. In this image data analysis speed, like vision transformer-based models are shown to be perform better than the traditional CNN-based model. So we want to investigate how we can use this transformer-based model for our audio data analysis. But one problem with transformer-based model is that they are tends to know as have a larger parameters, so they are big in model. So it might not suitable for the edge devices. So in this research, we use lightweight transformer-based model for the audio data analysis. So this is the overview of the system. First, we create a data set to get the ground truth. Also to get the label, we use the video data and the audio data. And then we create a audio-only data set. Then we train our transformer-based model on our data set. And then we expose the return model and use them during the inference time to do the detection. Together with the detected vehicle numbers and the sensor data, we send to the cloud through the MQTT protocol, and then do visualizations and then create digital twin instance. So these are the two prototypes that we use for monitoring. So we create two edge devices, one with the GPU capability, which is based on NVIDIA Jackson, and another without the GPU capabilities, which is based on Raspberry Pi. And then these are equipped with microphones, environment sensor, gas sensor, and PM sensors. So to create a data set, first we collect both audios and videos and audio into the MP4 file, and then we split into videos and audio data. Since we cannot get like vehicle data and numbers of vehicles, we cannot extract this information directly from the audio data. That's why we use, for that, we humans have to label them individually. So it takes quite a lot of time. To fast-time this process, we use object detection model, YOLO V8, to fast-time this process. So YOLO V8 detect the vehicles, and it gives the types, the onset and offset of the vehicles, and then how many vehicles go through. So by using this label, we were able to create the data sets. So we collect our data set at the road, which is one direction, 2 lane roads. So we collected around 1,000 samples, and each sample is like a 10 seconds audio clip. So during our around 3 hour data collection, we were able to record around 500 vehicles. So after we create a data set, we extract the features from the audio data. First, we check our audio clips is 10 seconds or not, and then we extract mass spectrogram as features. Since our audio data contains the environment noise as well, so we're trying to reduce that by removing the background noise. So to get the numbers of vehicles, we use 2 methods. In the first method, it is simple. We extract the audio features from the 10 seconds audio data, and then we feed it to our transformer model, and the model trying to predict the numbers of vehicles. In the second approach, instead of doing that directly, we divide our 10 seconds audio data into smaller window of 1 second. And then the model trying to detect what type of vehicle is present in these smaller windows. And after that, by whether depending on the vehicle present or not, we count the numbers of vehicles. So in this approach, we detect the vehicle type instead of directly predicting the numbers of vehicles. So one good thing about this approach is that we can get the number of vehicles according to their types. So we use F1 score and also related vehicle counting error to evaluate these 2 methods. So as a result, so this is the evaluation for our first method. So we tested 3 transformer-based model and 2 traditional-based model. And we also tested the different size of the model. So in this approach, one of the transformer-based model, which is SVDI, able to achieve F1 score of 0.7 and error rates of 0.185. In the second approach, we were able to achieve higher F1 score, also the lower error rates. But in this approach, sadly, traditional base model, ResNet 18, performed better than the transformer-based model. So even though it performed better, the transformer model performance is also very comparable. For example, one of the best performed is the mobile VDI, which is around 9.5, which achieved F1 score of 9.5. So after we do the analysis, the cost of transformer-based model performed poorly on this approach is that we only recorded 500 different vehicles. So our data set is very small. So transformer-based models usually have lots of parameters, so they tend to overfit. So because our data set is small, the transformer-based models are overfit on our data. So in the future, with larger data sets, we may be able to improve the result. So next, we also compare the time to do the detections, also sending the data. So with the H5, which has GPU capabilities, it can perform detection and sending messages to the cloud within 3 seconds. But for the device without the GPU capability, it takes quite a long time. For example, if we use bigger model, it takes much more than 10 seconds. So it is not very good. But if we don't use very large model, we can still achieve the desirable performance. If we use a smaller model, we can do with under 5 seconds. So if we want to reduce the cost, we can use lower capable device like Raspberry Pi with a smaller device, smaller models, with trade-off between accuracy and detection time. Next, we evaluate the power requirements. We tested two scenarios. In the first scenario, we do all the pre-processing and detection at the edge. In the second scenario, we do data collection at the edge, data collection only at the edge, and other pre-processing and detections are done on the cloud. So if we do the asynchronous approach, if we want to send the vehicle data and other sensor data, we can send into the single MQTT message, which is around 340 bytes. And if we want to send them in real time, which is under 10 milliseconds, we can send, we only requires 0.02 megabit per second. But in the cloud-centric approach, because we have to send the audio data as well as the sensor data, the data size became big and it was around 1.8 megabytes. So if we want to send them in real time, we require around 150 megabit per second. So by doing the detection at the edge, we can reduce the power requirement. So in conclusion, in this research, we try to detect the traffic intensity based on the audio data. So we explore two methods, and our second method able to achieve lower error rates and higher F1 score. And by putting more computing power at the edge, we can reduce the detection time as well. And by doing the detection at the edge, we can reduce the privacy issue as well as we can reduce the power requirements, which is important for the edge device because transmitting data can consume lots of power. So this is end of my presentation. Thank you for your attention.